In this segment, I want to show you how to estimate point-to-point or line haul distances. So the first question you might have is, why bother? Haven't we been around long enough, and aren't there enough tables and maps that have mapped the distance from every point to every point? Well, to be honest, no, because there's always new points that people want to go from and go to. Also, in computers, it's usually quicker to calculate than it is to do a table lookup. So there's a lot of reasons why people might want to do an estimation for this point-to-point distance. So how do you do it? Well, it really depends on what the network looks like that you're operating under, what the topography of that region looks like. And there's three big classes that we consider. The first is that Euclidean space that we've talked about in the past. It's like a tabletop. So the distance between points A and B is simply the square of the differences in the x and the y coordinate summed and then the square root. So pretty straightforward. This is also called an L2 metric because I'm squaring the differences of the x and the y coordinates. Then you can look at the grid metric or Manhattan metric. And it's called Manhattan metric because if you've ever been to New York, in Manhattan, the streets are all lined up like this, more or less. So on a grid, this is also called an L1 metric because the differences are just taking the absolute value, the power of 1. And so if I look at these, the distance on the Manhattan metric between A and B will always be longer than the Euclidean distance, right? Because I can only go in the x direction or the y direction. Makes sense. However, in the real world, for most cases, you have something like this, a random network, and you have to do a slightly different approach. So let me talk about that. For a random or a real network, what you're going to do to find the distance from A to B, to estimate this, capital D, you're going to take this circuity factor, this k factor, and multiply it by the direct distance from A to B. That's kind of the as the crow flies distance. So on a map, if I drew a straight line between point A and B, that would be that lowercase d. That's that distance, direct distance between the 2 points. Now I can get that in two different ways. If it's a small space, like within a city, within 10 miles or so, within 15 kilometers, then I can just use Euclidean. I can just say, okay, this is, if I was a crow and I was flying direct point to point, it would be roughly 5 miles, whatever. I would use that as my lowercase d. For longer distances, though, you have to recognize we're on a sphere. We have to use the great circle equation. And this is for any location that is more than 15 miles, 20 kilometers, something like that, anything that's large and within the same hemisphere. And so you see the equation here. It uses sines and cosines and arc cosines, and it uses the latitudes and longitudes. And so what it's really doing is finding the 2 points on a sphere. What is the distance between those? The direct distance. If the crow could fly across the hemisphere, how would it fly? What would its distance be? And the latitude and longitude are in radians. And so you need to convert, and if you have them in degrees, into radians, and you simply multiply it by pi over 180. So best to use in a spreadsheet. Wouldn't do it by hand too much. So what do I do with this? So I find the direct distance, and then I'm going to modify it by this k factor. So how do you think you get this circuity factor? Well, one way is to actually go and do random points. And in the next quick question, I'm asking you to do this. So you pick point A, point B, find the actual distance, find the great circle distance, and take a ratio. And then you can find for a common region, what is the k factor of that region? Because that k factor, the circuity factor, is really a function of the network. If I have a really dense network, my k factor will probably go down. So if I have very sparse roads, if I'm looking at, say, Australia, and there's things around the coast, but there's not a lot of roads in the interior, then that k factor will probably go up. So think about what the ranges are for this k factor. This is a good thing for estimation. What do you think the smallest k factor could be? So for straight distances, it can't be any lower than 1. Hopefully that makes sense to you, because if it was lower than 1, then that means I'm shorter distance than Euclidean distance. I'm burrowing into the earth, right? So you can't have a k for security factor less than 1. What about the upper range? Well, gosh, there really isn't one. but generally we'll see, I'll give you some numbers in a second, it can be as high as 2 or even higher. So it's twice the distance than the direct distance. That'd be a really tough network. And what are some cautions for this approach? Well, you have to make sure as I go point to point that I'm not crossing a major lake or a sea or an ocean, because obviously that doesn't make sense. So it's an estimation. It should be used with caution, but it's very quick. And let me just show you some numbers. This is a study done by Dr. Ron Ballou, and he published this. It's been a couple years, but what's interesting is it shows these K values and the standard deviation for the observations that they made for a number of different countries. So any of you Kiwis out there from New Zealand, you should not be surprised that your K factor for security is so high, 2.05. And Egypt, I've never been to Egypt, but look at that, very high. Look on the other end of things and look at Italy, and they're very connected at 1.18. So essentially what this number is doing, it's a multiplier against the shortest as the crow flies distance for what the expected distance would be between 2 points in each of these countries. So for the United States, we give the east of the Mississippi, west of the Mississippi, and then Alaska, which is much larger and separate from the lower 48 states. And you see it's much higher K factor. That makes sense because there's not a lot of developed roads up there. Okay, so this gives you an estimate of how to get a point-to-point distance. You find the direct distance, and you modify it by the circuity factor.